Here we will look at another application of Faraday's law. So we start with a table here. You could imagine cutting a hole in the table. So we just make a hole in there. Now, I'm going to drill a hole through here. And we're going to slide an axle into there. But before we do that, we're going to put a magnet in here. So a permanent magnet. And on that axle, we'll mount this permanent magnet. Okay, I'll put a little crank handle out here so that we can turn the magnet. Okay, now we're also going to add a wire. So we're going to take a wire from off the edge of the table here, and then we'll just go around the edge of the hole. And then back off. Now we want to think of this as the positive direction for current. So we know that the area vector should be pointing up this way. Okay, the area of that coil. While the magnetic field is off going this way at some direction. Okay, now if we rotate this magnetic field, then the flux going through that loop will change. And so we'll end up with some induced EMF on this, like a battery pushing the current in that direction. So it's called the angle between these theta. So if we draw them from the side here, we have the area vector pointing up, magnetic field vector pointing at some angle, theta relative to that. Now since that angle is going to be changing continuously, we imagine that the angle changes at a constant rate. So we'll just be spinning it without stop. Now we know that in order to calculate the flux, we need to take the dot product between that area vector and the magnetic field. So we need to get the parallel component of the magnetic field, which is just the magnitude times the cosine of that angle. So then we could write this, the dot product will just be the product times the cosine of that angle, which is changing in time. That allows us, in turn, to calculate the induced EMF, which is the rate of change of that flux. Sorry, this is the flux. The magnetic flux. So there's a couple minus signs here which change. There's one minus sign from the derivative of the cosine and another minus sign over here. Okay, so we find that the induced EMF is this sine wave that oscillates in time. So this is the basic structure of how electricity is generated. You have something which has mechanical energy, which is able to turn this crank. So if it's hydroelectric, then you have the power of the water turning some kind of wheel. which rotates the... you can either rotate the coil or you can rotate the magnet. And so what's generated is a current with some voltage, the induced EMF. So now we can imagine if we put some kind of load, which we model as a resistor, connected to that, that will allow the current to flow, and we'll get power in that. In this case, okay, so that would be now the question is, where does that power come from? Okay, of course we know it comes from the cranking of that arm, but it's a little hard to see what's the connection there. Why is it any harder to crank the arm if there's a wire there surrounding it than if the magnet was just spinning on its own? And we know if the magnet's just spinning on its own, it's not that hard to crank. So, I mean, there's not too much friction in the bearings. So the thing is that if there's a current going in this loop here, we know that a current in a loop in a magnetic field experiences a torque. So let's look at that torque. Okay, so the torque we found this before. The torque on that loop is the current times the area of the loop times the magnetic field going through the loop and the angle between that area and the magnetic field. So in our case, we know that that angle is changing with time, so we'll write it that way. All right, so now we know that our current depends on our load resistor, how much our load is, and also on the induced EMF. But our induced EMF, we just calculated it. It's just this. So combining these two, we find that the torque, just the product of just substituting this into that equation, we see that we have two of these BA sine omega t's. So we've got an omega b squared a squared sine squared. Okay, now that's the torque. Now, if you remember, the amount of power it takes to drive something like that is, you can use the same law we use for linear motion. So what's the amount of work done? The amount of work per time, that's the power, is the force times the displacement over the time. So this is the force times the velocity. And it works the same for torque. So for torque, the amount of power it takes to drive will be the equivalent of force for rotation as the torque, and the equivalent for velocity is the angular velocity. So if we take that and put that in this equation here, we end up getting the omega squared also. So now we get everything in the top squared, so we can write it like this. But lo and behold, that's exactly what we got up here for the power delivered to the load. So our electrical load gets an amount of power that's exactly equal to the amount of mechanical energy used to drive the crank. Of course, this is an ideal situation. There is always some losses that we're not considering here. Okay, so but this is basically how electricity is generated. Pretty much everywhere in the world there are some new techniques, but this is the main way. So okay, so let's look at another example. This is wireless charging. Maybe if you have a newer phone, you don't have to plug it in anymore to wire. You place it on top of a charger, and somehow it charges it through there. Or the electric toothbrushes are the same thing. You put it on a little stand, and it charges the toothbrush. The same method in both. So in this case, what we have is exactly the same thing. So the charging plate is really just another loop connected to some oscillating voltage supply. Okay? And the phone is a little more complicated, but it also has a loop which induces an EMF on it, which drives some current through what's called a rectifier that turns it from being alternating to direct current, and that charges the phone or the battery. It's not very complicated. Essentially, it's two loops, one in the phone and one in the charging plate. The one in the charging plate produces a magnetic field that pierces the other one and causes induced voltages. Now we actually already saw this. This was the first example we did when we were trying to show Faraday's law. So if you think about it now, what we had was this charging coil, the one in the back, that's connected up connected up to this power supply here. So this back one is connected up to the power supply. And then we had the coil in the front. That's like the coil that's inside your phone. Okay, and then this readout here, this was the voltage on the phone. This wasn't the voltage on the coil, but actually the voltage on the coil is proportional to that current as well that we were reading there, or the field that we were reading there. This same structure of two coils laid on top of each other is also the structure of a transformer, or the wall wart, as it's commonly known. So you have the 120 volts in your socket in the wall, and you need to convert it down to something that your electronics can use, say 9 volts. And it's basically the same thing. You just got two sets of coils laid on each other. And the idea is by adjusting the number of turns in each coil, you can change the voltage at the output. So for example, you can there's a common transformer, is to go from 120 volts down to 9 volts. At least ideally, the relationship between them is very simple. The ratio of the output voltage and input voltage is the same as the ratio of the number of turns on the output coil to the number of turns on the input coil. In practice, this is not a very accurate equation. There's a lot of things that are not ideal. Not all the field going out of one coil goes into the other, and there's other losses and resistances and things. But the basic idea the trends are about right.